Hello, this is Dr. N. Amudapriya, Associate Professor Chikli, Rohini College of Engineering and Technology, Palkulam. We are here to discuss about the transmission and distribution subject of Regulation 2021, and lecture covers the methods of grounding from the Unit 3. What is grounding or earthing? Normally, the process of connecting the metallic frame which is not carrying any current of the electrical equipment or some electrical part of the system, normally the neutral point to the earth. It's called grounding or earthing. There are different classifications, namely equipment grounding and system grounding. Equipment grounding deals with the earthing of the non-current carrying metal parts of the electrical equipment. So it is based upon the equipment. System grounding means earthing some part of the electrical system, earthing of a neutral point or star connected system in generating stations and substations. So system grounding is normally the process of connecting electrical part. Here the ungrounded neutral systems may be responding in a greater way. In an ungrounded neutral system, the neutral is not connected to the ground, that is, the neutral is isolated from the ground. Such a system is known as a free neutral system. So in ungrounded neutral system, the line conductors may have a capacitance between one another and to the ground. To one another and maybe a ground. And the delta connected capacitance have little effect on the grounding characteristics of the system, and this can be neglected. So let us consider about the star connection alone. Next, while considering the neutral grounding process, which is used for grounding the neutral point of a three-phase system to the earth, either directly or using some circuit element. What is the advantages? This can have a healthy phases to have a limited, the voltage will be within the limits. The high voltages due to which the grounding occurs can be eliminated. The protective relays can be used to provide a protection against earth faults, and the over voltages due to the lighting discharged to the earth, and this provides greater safety for the personnel as well as the person's human and the equipment. This provides a service reliability. While considering the operating and the maintenance expenditures, and this may be highly reduced. Regarding the methods of neutral grounding, let us have it as solid or effective grounding, resistance grounding, reactance grounding, and heaters and coil grounding. While considering all these four types, each and every type is important at different cases. The choice depends upon many factors. It includes the size of the system, system voltage, and the scheme of protection which are in need to be used in that particular system. Condition. Next is a consideration of the first one, which is a solid grounding or effective grounding. Here we are going to connect a line or a wire directly from the neutral to the earth, to the socket. So in this case, the system may be a three-phase generator or three-phase transformer, etc. This solid grounding is very effective because the neutral is effectively held at the earth potential. So no arcing ground or over voltage conditions will occur. If there is an earth fault, the healthy phases may remain at normal phase voltage. This permits to insulate the equipment for phase voltage. Hence, the cost saving is an optimal one in this case. Also, it becomes easier to protect the system from earth faults which may occur frequently in the system. Disadvantages: if suppose there is a large number of severe shocks, the system may get into instability. And next, if heavy earth falls are flowing through it, then the circuit breaker contacts may burn off. The greater interference with the neighboring lines is also possible, and there can be certain measures which can reduce these disadvantages. Application: it is employed where the circuit impedance is sufficiently high so as to keep the earthfall current within the safe limits, that is at 33 kV or 5000 kVA. Next is the resistance grounding. It is nothing but the resistance is being connected at the line which is connecting the neutral to the earth. This is what is called resistance grounding, and the name depicts it. If R is very low, then the system is called solid grounding system. If R is very high, then it may go for as an ungrounded neutral system. So the R value has to be selected to be within a limit, that is the earth fault should the earth fault current to 2 times the normal full load current. So this is the value for R. By adjusting the value of R, the many arcing grounds can be minimized. Many different values can be minimized. Interference with communication circuits can be reduced, and it improves the stability of the system. The main disadvantage is that the energy cannot be stored in the resistor. It will be dissipating into heat. So that's the main disadvantage. In application, it can be used for voltage of 2.2 kV to 33 kV with a capacity of 5000 kVA. Next, let us see about reactance grounding. The main purpose of the reactance grounding is to replace the resistance so that the power will not be dissipated too much. It can be stored and then discharged, etc. This is what is the reason for using this reactance grounding. And then by changing the value, earth fault current can also be changed to obtain the condition similar to that of solid grounding. But the main disadvantage is that protective devices, the fault clearance it requires to operate the protective device is high cost is higher than that of the resistance grounding one. Some for specific fault conditions, if it is a higher one, then the cost will be high. High transient voltages may appear under fault conditions. So these are some of the disadvantages. And next we can go for arc suppression coil grounding. This is a better method when the value of the inductance of arc suppression coil is such that the fault current exactly balances the capacity current IC. It is called resonant grounding. Suppose the arc suppression coil, if it is connected between the neutral and earth, it may be of a iron core coil. Why it is called iron core is this Peterson coil is meant to bear with different fault currents. So its strength has to be increased, and hence iron core coils are being used. And the reactor which is provided with the tappings to change the inductance of the coil is being highly emphasized here. By just changing the tappings of the coil can be tuned with the capacitance. Hence the resistance grounding is very effective in this case. So these are some of the values of IR, IC, XC, IF, etc. And this is how we will calculate for the resonant grounding. IL is equal to IC, L is equal to 1 by 3 omega square C. The various advantages is we can prevent the damage of arcing ground to the maximum, and the main advantage is the underground neutral system will be having some advantages of underground neutral system. Main disadvantage is that due to varying operational conditions, the capacitance may change from time to time, and hence therefore inductance of the Peterson coil has to be readjusted. The lines should be compulsorily transposed. While considering voltage transformer earthing, this is simple. We are connecting a voltage transformer, potential transformer at the neutral. So the primary is being directly connected to the neutral, and a low resistance in series with the relay is connected at the secondary side. So this will be very effective, since an earth fault, if suppose an earth fault on any phase produces a voltage across the relay, this will flip the circuit. So automatically there will be a reduction in the impact of the fault. So the transient over voltages on the system due to switching and arcing grounds can be highly reduced. And this type of earthing has all the advantages of ungrounded neutral system. Arcing grounds can be eliminated. The main disadvantage is that the system insulation will be overstressed due to the occurrence of various different types of faults. And while considering the applications, they are being used for confinement of the generator equipments which are directly connected to the step-up power transformers. While considering the grounding transformers, that may be of different connections. If it is a 3-phase 3-wire system, or if it is for 3-phase 4-wire system, it will be it can be connected in a 3-limb structure. Each limb of the transformer is an identical one because the windings is the same, where the directions of the current in the two windings on each limb are opposite to each other, go and return coil. Under normal operating conditions, the total flux in each limb is negligibly the smaller one, and therefore the transformer draws very small magnetizing current with the voltage remaining balanced as it will be a 4-wire system. And normally load current, unbalanced load current is relatively small. Even when the fault current is quite high, we can have the impedance of the grounding transformer is very low. Under normal conditions, if suppose if the losses are continuously occurring in the ground transformer, then in such a case the high fault current will also produce copper losses in the transformer. Since the duration of the fault current is generally between 30 to 60 seconds, the copper loss will occur only for a short interval. So this may be reduced to the maximum level. This is what is the thing while considering this type of connections. The star type connections may help in reducing the loss impact. Thank you.